Welcome. So in this tutorial, I'll be talking about the Bpsk modulator, and this is one of the major parts of this circuit. So we are actually talking about the Bpsk transmitter receiver. So the Bpsk modulator is actually the Bpsk transmitter, because it's the modulator which actually modulates the input signal and then sends it out to the receiver, and the receiver is the demodulator which recovers the original input. So the first part of this circuit is the clock divider we've been talking about. So this is essentially the clock divider, and the output of this divider goes here. You can see where I inserted another line of clock, and this is another clock, which is the system clock. This one, let me highlight, this one is the system clock, and this one is the output of our clock here. So remember, as we spoke earlier when we were talking about the delta sig modulator, the clock is actually 10 megahertz and the system clock is 200 megahertz. So by now, when you do the calculation, it's somewhere division around 4 or 50. So that is that about this first part layer of the circuit. Then this place is the sequence counter, and this is the sequence generator. The sequence generator here and the sequence counter. You see all these things in the code. So what this RAM 5 is, a 5-bit of RAM. It counts from 0 to 19 and it resets itself. This 1 to is hexadecimal. In decimal is 19. You can see it here. In decimal is 19. In hexadecimal is 13. So Logisim is actually taking the value in hexadecimal. So whenever it compares it with what is stored here already, what is stored in the RAM. So if by any chance is equal to 19, it triggers this multiplexer and it resets. Then else it increments. So it's a counter, 0 to 19 counter. So is a sequence counter, and whatever is counting is used to control this demultiplexer here. Sorry, this multiplexer is not a demultiplexer. I actually rotated it. I rotated it 90 degrees anti-clockwise, so that's why it's facing up. So it was conservation of space. So, but the output, consider output is controlling this multiplexer here, and the output of this multiplexer is stored here. So this RAM 8 here is called the sequence generator, and these are the sequences. So whenever this RAM here is incrementing 1, 2, 3, 4, 5, 6 to 19 and the resets, is actually feeding it to this multiplexer, which is likewise moving from each of these values here, 1, 2, 3, 4, 5, 6, 7, 8, till when it gets to 19 it starts afresh. So you can see the values are in hexadecimal. The values are in hexadecimal, and you can see them as 7F, A6, CA, E6, F8. In decimal, this is what the sequence generator actually looks like here. This is it. So this is a sinusoid that was breaking down into compartments. It started from 127 to 127. It goes from 127, it increases up to 254, then it goes back to 127, then it keeps going down till it gets to 0, and then it goes up back to 127. So this is how this sequence generator is working. So as it's incrementing, it's going from 127 to here to here to here to here to 254. Then the values will keep declining to 127 again, keep going down more to 0 and back to 127. And once it gets there, it continues again. So it's a sinusoid. It's going like this, like this, like this, like this, like this, so without end. So I'll show you how we use this to modulate our input. So later in this tutorial, but just know that this is the sequence generator and this is how it moves, like this, like this. So that's why it's 19. When you count the values here, they are 19 total. So these are the values in decimal, whereas they are written in hexadecimal. So this 7F now is 127. Now it keeps going till it reaches here, then it starts afresh again. So the output, I will show you how the output came out here, and when we keep going down this circuit, I'll show you how we use the output down the circuit. So that's the sequence we'll be using. So depending on the resolution you want, you can as well make here 254, then the 254 now go up to 512, come down to 254 again, come down. So depending on how the resolution you are using. But I think whenever you see this arrangement, you should have known how the counting goes. So now this is an interrupt. This int bit here is the input. Here is an interrupt. It means interrupt to send. So whenever it comes in, it means that data is about to be sent. Okay, and I'll show you how it works. So this particular setup here, we made something like this when I was dealing with the FPGA circuit to trigger one shot triggering. So, and this is how it works. So this int comes here and goes into this is a RAM 2 bits. So it goes into bit 0 here, and then on the next clock cycle is stored and it shifts to bit 1, and then it goes, and that one goes down to bit 1. Let me zoom in so you see what happens here. Sorry. It's okay now. So it first of all goes into bit 0, right? Then on the next clock cycle, the int bit that went into 0 will now shift to 1 to bit 1 on the next clock cycle, leaving the bit 0 open. This is the new bit 0 again. I don't know if you understand. So this is the initial bit 0. This one will now go to bit 1 and then take another input here as into its bit 0 here. So assuming the first one that came, which is this one, triggered it as 1, then the next one, which is this one, will now trigger it as 0. That is what this is trying to measure here. So here you can see that the bit 1 here is the first one, then bit 0 is the second one. So it's saying if it has not happened before, that is if bit 1 is still negative, that is if it's still 0, and then the interrupt comes on, trigger the interrupt. So this is how the interrupt was triggered here. I don't know if you understand this. this is what I describe as one shot triggering. This is where the output of the triggering comes here. So it compares